Hi, my name is Shriti Dham, and I research utilizing machine learning to find a more sustainable alternative to polyester in textiles. So, firstly, I want to give a special thanks to my mentor, Mr. Shomik Verma, for all his help throughout this process. And a little bit about me. I'm a junior at Northgate High School in the Bay Area in California, and I play tennis on the school tennis team, and I love to do art. As well, my favorite subjects in school are math and chemistry. And I researched this specific topic because I was interested in blending sustainability and environmental science with modern technology like AI. And I have a bet for you. I bet you that if you check the tag inside of your shirt, it is at least 20% polyester. Am I right? Well, it doesn't matter because if your shirt isn't, the person sitting next to you probably is. So, first of all, what is polyester? Well, it is a type of plastic, more specifically, a thermoplastic. Thermoplastics are easy to mold after heating and reheating, and therefore it is found in textiles very often. A polymer in general refers to a material made up of a chain of repeating units called monomers. Here, PET is a common polyester in clothing, and this is what the polymer for it looks like. And you can see the repeating units, or monomers. So, polyester has a heavy toll on the planet. This is due to the vast amount of it produced, over 50 million tons per year, and its production releases harmful greenhouse gases into the atmosphere. Polyester is also known for fueling fast fashion products, so the dangers of microfibers released in wastelands is quite prevalent, which affects wildlife, soil, and bodies of water. Here is a visual representation of the production process of polyester and the different negative impacts that each step of the production process has on the environment. You can notice that the last part, like dyeing and distribution, can lead to land pollution, air pollution, and water pollution. So, how can machine learning help with this issue? Well, we can use machine learning to predict a new polymer that is possibly more sustainable. Machine learning uses graph neural networks, which is depicted on the right, where you can see that an output is predicted when it is fed an input. Machine learning is a game changer. It improves speed of experiments, reduces costs, and promotes sustainability. It is appropriate in this specific research topic as it will be able to grasp the large databases fed into it and generate predictions based on patterns that it recognizes within the data. So here is a flowchart with a visual representation of what the prediction process will look like using machine learning. First, data collection, then data processing, then the model training, and finally, property prediction. So the data curation was a two-step process. The first step involved gathering databases of polymers with corresponding property values. The polymers in the database were given in a kind of code called smile strings, which are written in a way that reflect the polymer's chemical makeup. The image on the right shows a screenshot of one of the databases that has a corresponding value and the polymers written in the smile string format. Once we trained a model on the property value databases, that model sifted through a much, much larger database with 1 million polymers that didn't have a corresponding value attached to them. And the model predicted the desired property values for each of those 1 million polymers. In order to evaluate the accuracy of our predictions, we graphed the mean absolute error, which is a measure of errors in predicted values. The graphs of the mean absolute error compare the true and predicted values on the graph. So on the left side of the screen is the glass transition temperature mean absolute error graph, and on the right side of the screen is the density mean absolute error graph. The linear patterns depicted in both graphs shows greater accuracy because the predicted values are close together with the true values. Next is the melting temperature mean absolute error graph and the oxygen permeability mean absolute error graph. Note that the oxygen permeability true versus predicted graph on the right has very few plots, and this is just due to the small size of the dataset compared to the other datasets, not because it is less accurate than the other datasets. The properties plotted in all of the graphs, including this compressibility temperature true versus predicted graph and bulk modulus true versus predicted graph, are all of the desired characteristics within textiles. And then we started the screening process. So the screening process involved finding the polymer closest in value to polyester. And this chart right here shows polyester's values for each of the desired products that we graphed earlier: density, melting temperature, oxygen permeability, compressibility, bulk modulus, and glass transition temperature. So to find this most similar in value polymer, we screened all the predictions from the large 1 million polymer database. We were looking for the polymer that had property values closest to polyester's property values. So here's a chart that gives a visual representation of what the screening process looked like and the code looked like. And the polymer prediction values were scanned in relation to the true polyester values, and then our code highlighted which polymers had a close or the closest match. So the screening showed that the closest polymer in value was this polymer on the screen here, which is written in the smile string format that we went over earlier. So here's the closest in value polymer compared to polyester's true values. And many of the values are quite close, as you can see from the chart, but with the exception of oxygen permeability, which is over 40 units off. So the prediction process gave us a polymer closest in value to that of polyesters, but its sustainability would still need to be evaluated with real-world experimentational processes. So if the polymer is more sustainable, it can greatly decrease the environmental impact of textile production and have an impact on the fast fashion industry and even other products that use polyester as their principal material. This image here illustrates the experimental processes necessary when determining the sustainability of the found polymer. And some of these include waste residues of the polymer, taking that into account, also how impactful the engineering of the textile is, the life cycle of the polymer, and how recyclable the polymer is. Thank you for listening. I'd love to hear any thoughts or questions.
Hi, how are you? Great job. Okay, I do have a question here. What are other things that you think we could use machine learning for in environmental science?
So machine learning, of course, so for this project, we predicted values of properties based on ones that relate directly to like properties of textiles, like oxygen permeability would relate to like the breathability of the textile. So we can plug in different types of property values into the machine learning, like hardness and toughness ability, and that could give us different types of polymers being predicted with different values that could be used for other types of products like plastic bags or plastic packaging. So it really depends on the properties you plug into the machine learning model.
Oh, okay. Interesting. What skills did you develop that you didn't anticipate learning during this project?
So in this project, there were many roadblocks, so you had to think out of the box. I think that is a major skill that I improved on when doing this project, because in the code, not everything would work out the way you wanted it to, and you might run into errors. And most of these errors you can find out by going into the fine print of the code and looking into small errors. But sometimes the code just would glitch or not work out the way you anticipated. So what you need to do is find a different way to code it to get to the same result. It kind of reminds me of what I do in math. Sometimes my math teacher like teaches me a certain way to learn a problem and get an answer, but I can still get the same answer just by doing the math a different way. So this is kind of similar. You can still get the same result just by coding it a different way if you run into a roadblock.
I love that. And I also love the resilience that you're learning by you hit a roadblock and you try to go a different way. So I appreciate that as well. Okay, I'm going to remove the spotlight from you. So congratulations to all of our speakers. You guys all did a fantastic job. I feel smarter just from listening to you. Wait, okay. Oh, wait. So we now have a question. One last question. What was the most surprising roadblock you found?
So in the code, when we were training the model, like for a while, it just kept not getting us to the right like training model that we expected. So I thought this would be like probably the easier part of the code as we were just kind of training the model before we actually start plugging in and screening all the code. And then this is where we had the most trouble. So that was really surprising.
Okay, thank you.